Influence diagrams. As in Chapter 3, we generalized from probabilities to actions with risks. Influence diagrams are graphical models that allow the generalization of graphical models to include decisions and utilities. An influence diagram contains chance nodes representing random variables that we use in graphical models. See Figure 16.16. It also has decision nodes and a utility node. A decision node represents a choice of actions. A utility node is where the utility is calculated. Decisions may be based on chance nodes and may affect other chance nodes and the utility node. Inference on an influence diagram is an extension to belief propagation on a graphical model, given evidence on some of the chance nodes. This evidence is propagated, and for each possible decision, the utility is calculated and the decision having the highest utility is chosen. The influence diagram for a classification of a given input is shown in Figure 16.16. Given the input, the decision node decides on a class, and for each choice, we incur a certain utility risk. Notes: graphical models have two advantages. One is that we can visualize the interaction of variables and a better understanding of the process, for example, by using a causal generative model. The second is that by finding graph operations that correspond to basic probabilistic procedures such as Bayes' rule or marginalization, the task of inferences can be mapped to general-purpose graph algorithms that can be efficiently represented and implemented. The idea of visual representation of variables and the dependencies between them as a graph and the related factorization of a complicated global function of many variables as a product of local functions involving a small subset of the variables for each seems to be used in different domains in decision-making, coding, and signal processing. Kashchan and Frey and Lollinger in 2001 give a review. Now, the complexity of the inference algorithms on polytrees or junction trees is determined by the maximum number of parents or the size of the largest clique, and when this is a large, exact inference may be infeasible. In such a case, one needs to use an approximation or a sampling algorithm. Variational approximations and Markov chain Monte Carlo MCMC algorithms are discussed in Jordan et al. In 1999, McKay in 2003, Andrew et al. In 2003, Bishop in 2006, and Jordan in 2009. Graphical models are especially suited to represent Bayesian approaches where, in addition to nodes for variables, we also have nodes for hidden parameters that influence the observed variables. We may also introduce a hierarchy where we have nodes for the hyperparameters, that is, second-level parameters for the priors of the first-level parameters, and so on. Hidden Markov models is one type of graphical model, and actually any graphical model can be extended in time by unfolding it in time and adding dependencies between successive copies. Such dynamic graphical models find application in areas where there is also a temporal dimension, speech recognition. For example, in fact, a hidden Markov model is nothing but a sequence of clustering problems where the cluster index at time t is dependent not only on observation at time t, but also on the index at time t-1. And the Born-Wilk algorithm is expectation maximization extended to also include this dependency in time. In section 6.4, we discussed the factor analysis where a small number of hidden factors generate the observation. Similarly, a linear dynamic system may be viewed as a sequence of such factor analysis models where the current factors also depend on the previous factors. This dynamic dependency may be added when needed. For example, Figure 16.5 models the cost of wet grass for a particular day. If we believe that yesterday's weather has an influence on today's weather, and it tends to be cloudy on successive days, then sunny for a number of days, and so on. We can have the dynamic graphical model shown in Figure 16.17, where we model this dependency. The general graphical model formulation allows us to go beyond the power of HMM proper and lead to improved performances, for example, in speech recognition. Zweig in 2003, Biomis and Bartel in 2005. Graphical models are also used in computer vision, for example, in information retrieval. This is by Barnard et al. In 2003, and scene analysis, Sanders et al. In 2008. A review of the use of graphical models in bioinformatics and related software is given in Dunkers and Troyos in 2008.